Steve, when you want, Steve.
Okay. Um, First of all, hi everybody. It's we've come a long way here. I was going back over the topics that we've covered, and it's really quite a gamut that we've been through together. But one of the things that we haven't talked about yet is actually the beginning of one of the most important threads of astrophysical study, and that's variable stars. But variables in a particular way. Everything we've been talking about varies. Um, for one reason or another, the universe has transients on a lot of different scales, mostly either at birth or death stages. But one of the things that was a striking problem in the 19th century, something that some of you will have probably suffered through in basic physics because of the way it's often taught, is this problem in thermodynamics that if you have a cylinder that you apply heat to, the and it can expand, it will expand. And then if you cool it, it'll contract, and you can actually set up a mechanical cycle called the steam engine with a cycle of input of heat and decrease of heat in a way that you could actually create a stable cycle, which, as long as it doesn't have to do work, could virtually go on forever. And if it does do work, is going to have to be resupplied. In other words, if you have a compressible medium, you can set the thing up in oscillation. And you might be thinking, what the hell does this have to do with stellar pulsation? In the beginning of the 19th century, when people talked about stars, and that's where the word stellar comes from here, when they talked about the variation of stars, it was always in the context of binaries. And because of that, because they were looking at problems connected with gravity, the easiest model that you could build for a star in a binary system is just bulk mass. You don't care about what its interior structure is because the thing you're trying to measure are dynamical, or the things you're trying to measure are dynamical properties of the system and not of the stars. And one of the things that was so characteristic of the 19th century was that before the application of spectroscopy, specifically before the last roughly third of the 19th century, the reason you were concentrating on what were called then liquid stars was twofold. First, if you have an object whose density is constant, in other words, a water bag, you can change the shape of that thing and use the condition that the surface is actually an equipotential, which means you can solve the gravitational field of objects of arbitrary shape as long as you know that their density is uniform. And that meant you could do things that were analogous to solving real world problems like gravitational attraction, like hydrostatic equilibrium. It was answering questions in geology. And ultimately, the thing that you could do with binary stars was, in the absence of any dynamical information, because you had no spectroscopy, you could get the shapes of the stars or the relative sizes of the stars by just looking at eclipses. And if you had the periods and you could say something about the relative sizes of the stars, for an awful lot of the 19th century, that was more than enough. Simply cataloging variability was something that was a kind of closet industry. Um, it was sort of in the back of the field that the main thing in astronomy in the 19th century was positional. And in that sense, finding that there were stars of various types that varied in brightness, whether they were strictly periodic or not, was really important because they would be specific objects that would show up in catalogs. And if the catalogs were taken at a single epoch and you have a variable object, then it's possible that in a future use of the catalog, there would be something anomalous in the particular population that it was representing. So in the middle of the century, when Argelander began at Bonn looking systematically at the sky, creating the Bonner Durchmusterung, which became the BD, which became one of the standard astrometric catalogs and one of the ones that served as the principal identifying collection of stars for any other work. It was an astrometric catalog and it was done visually, but in the course of repeated observations that were necessary for the astrometry, Argelander started accumulating lists of variable objects, having absolutely no idea what the periods were because they weren't observed with that kind of cadence in general, and basically having no idea what a variable star actually would mean. Remember, we're talking about the 19th century for a moment. This also became really important when it was realized that these were, in fact, in some cases, periodic. And so finding variable stars became a kind of mania, uh, especially in the last quarter of the 19th century with the introduction of photographic plates. Now, this is really important. When you have a photographic record, you can do on the plate relative measures of brightnesses of stars. Now, I hope you'll forgive a little digression here. It's not meant just for historical purposes. When you take a field with a CCD, you can do a flat field, and otherwise, the variation that you have across the field and the 0 point can all be taken care of digitally and separately from the image that you're working on. You can build up a master flat, for example, that gives you the characteristics of the CCD. And if you're doing photometry over a field, you know that since the field of view is relatively small, the sky over that field of view is going to be pretty uniform. So once you've corrected for the sensitivity of the CCD, unlike with spectroscopy and doing absolute calibration, since you know from other catalogs what the brightnesses of the stars are in the relative in the vicinity of any one of the points on your image, you can get the brightness, relative brightness of any star in the field. And you can also measure the positions directly because you have an absolute plate solution. The problem with photographic plates was much worse. Every damn plate was different. And you can't flat field a photographic plate. You can get clear plates, so you can get some idea of what the minimum sensitivity is. But in the part that's exposed, you can't determine what the fluctuations are of the background. And so the actual measurement of variation on photographic plates is really delicate, especially when the field hasn't yet been well calibrated. So you have to have ways of measuring in the field the brightnesses of a few reference stars. You all know this, but think about what would happen if every time you took an image, you got a different flat field. And every time you took the image, once you've actually analyzed the image, every star on the image could potentially be affected by the accumulation of developer or the lack of developer. In other words, this is a highly nonlinear process. And in that the measurement of variability becomes a real problem. You have to know what isn't varying. So when it was realized that from taking images of globular clusters and cluster stars, there were easily detectable variable stars from one plate to another in in globular clusters, and these in fact became known as cluster variables, on timescales of days, where you knew that the vast majority of the images were not changing, but you had a couple of objects, a couple of stars that you could actually resolve that really were changing. This became a major research project, especially at Harvard, and especially under Pickering, that one of the aims was to go through in the galaxy the so-called selected areas, which had been set out for astrometric standards as regions in the galactic plane and near the galactic pole that were of a special interest as just target areas. There were of order 100 of these scattered over the sky, originally identified by Kapteyn. It was for galactic structure. But one of the other projects was to go to the southern hemisphere and use the Arequipa station in Peru to take plates of the Magellanic Clouds, which at the time were clearly known to be stellar systems. There was no question about that. But to know whether they were part of our galaxy, the so-called island universe picture, whether these were separate or part of our galaxy, was actually a major problem. But with photographic plates, it was thought you could at least see what the population was like, get an idea of what the distribution of stellar brightnesses is. The whole shtick, this stuff that people do routinely now with CCDs. Basically, astronomers have, we're known to have very little imagination. So we tend to do the same thing over and over again, just with different instruments and different targets. And the Magellanic Clouds were especially interesting, in part because of the southern station, and in part because of the quality of the refractor that was being used to get the data. So these plates were then shipped back to Harvard, and they were analyzed by the staff there, among whom was Henrietta Leavitt, who was given the problem of doing the variability of stars in the Magellanic Clouds. Now, the last part of this, to make this last point, the cadence of these plates was not necessarily one per night. And any of you who have read about what the conditions were like at the end of the 19th and beginning of the 20th century at observatories in the Southern Hemisphere will certainly be sympathetic to the thought that you had to, on with mules, carry boxes of photographic plates up to the telescope at high altitude, develop the plates under the right conditions, somehow have the damn things survive the trip back to Harvard, in addition to having them get from the northern to the southern hemisphere. You weren't, again, think about what you're dealing with here, the physicality of the photographic plate being so different than creating a FITS file and shipping it over the internet. So the plate supply was limited, the developer was limited, the physical stamina of the observers was limited, and between all of that, hundreds of plates were secured, but not necessarily in any particular sequence. So it was already known that for the cluster variables, the typical timescale was days, but it wasn't clear that there were the same variables in the Magellanic Clouds, which had stars that were very much fainter. We're talking about 18th, 19th magnitude stars, which by the standards of the beginning of the 20th century was a real problem. With all of that, and then with the difficulty of finding periods by methods that were extremely primitive, very slow, and basically the equivalent of phase dispersion minimization, where you would plot the brightness and then try to figure out from fitting by hand, say, a spline through the points to get some kind of periodicity. Leavitt managed to do this for a sample of stars in the Small Magellanic Cloud, and the result was this paper, the Harvard Circular 173 in 1912, that showed here the period in days and here the brightness in magnitudes. And what she pointed out in this, in a paper that I should add, she did not sign. It was signed by Pickering, who was the director. But she found that when you took the maximum and the minimum brightness, because it wasn't always clear that you were getting the star in its whole cycle. So very cleverly, she did the best thing. She looked at the extrema of the statistical sample. And this is actually really clever in realizing that the average amplitude was about 1.5 magnitudes. In looking at this distribution, and this is something we do now also. Okay, this is something that can be done statistically when randomly sampling galactic fields. The difference between them was approximately constant, and the two extrema fit a line such that the magnitude was proportional to the log of the period. And this was unexpected uh, for a lot of reasons. First, in binary stars, there was no period luminosity relation. That unless there was something like a mass luminosity relation, which at this point hadn't yet been realized, and that was to come another 20 years later, the possibility that you would have a physical relation between the brightness of the star, which would be indicating not just the total luminous output, but presumably also something about the mass and the radius of the object and its period, smacked of something mechanical, but we'll say thermodynamical. But it wasn't clear immediately what was going on. Okay? On the other hand, even if it wasn't clear, there were some who were willing to stick their necks out. And this paper by Shapley and Nicholson, which, as far as I know, is almost unknown in the field, was a remarkable piece of intuition based entirely on what Leavitt found, that it was realized that in observing stars, specifically, I'll get back to this, but specifically Delta Cephei, which now was realized to be similar to the stars that were being looked at in the Magellanic Clouds. So obviously, because it was already known that Delta Cephei was periodic, it was originally thought that this was a binary star and that the period was actually the result of an eclipse of some kind until spectroscopy showed that it didn't work, that you didn't get zero velocity when the star was faintest, that there were shifts and it didn't fit the equivalent of an eclipse because the shape of the variation was wrong. But these guys, in a paper that appeared in the National Academy of Sciences, not even in the APJ, on the spectral lines of a pulsating star. Okay, this is 1919. They make the statement, we conclude from these results that it's doubtful if either the periodic broadening or the slight asymmetry of the lines due to the distribution of velocity over the stellar disk, in accordance with the pulsation hypothesis, can be observed in any method thus far used. Well, that was 1919. Within a very short time, it was realized that no, it actually could be observed, that the shape of the lines were not exactly the same as you would expect for a uniformly spherically pulsating object. Nonetheless, the amplitude was something that could actually be measured. Uh, and this is the progression of the field, which I think you can measure in monographs. Um, Usually in science, when you finally hit the stage of a monographic presentation instead of papers, it means that you're pretty advanced in the basics, that you've gotten to the point where there really are fundamentals. The first example of this was 1926 with Eddington's book, The Internal Constitution of the Stars, in which he actually mentioned the possibility that the variations that were being seen in variable stars of the Delta Cephei type fit the picture you'd expect for a pulsating sphere, that it was a thermodynamic process. By 1936, Payne-Kapashkin, who else, was already working on a monograph that appeared in 38 on variable stars, in which, like with her book several decades later on the galactic novae, in fact, 20 years later, systematized everything at the time that was known about the variability of these objects and pointed to the fact that stellar evolution was such that stars, not all of them, but stars at some stage in their lives appear to go through pulsational modes. In 1949, Rosalind, who actually had been Eddington's student and was responsible for the first calculations of radiation pressure in stellar interiors, but he was also at the time uh, one of the most important meteorologists in the world, wrote the pulsation theory of variable stars, which is still in print from Dover, that set out how to calculate the interior behavior of a pulsating star, but still lacking fundamental ingredients, understanding what the interior was. And that was, I think, first systematized in John Cox's book, The Theory of Stellar Pulsation. So you see a trend here covering a period of, oh, 60 or so years, that you have the discovery of the period luminosity relation and the possibility that you could study the spectroscopic variability of these objects before Eddington's book, so at the beginning of the 20s and end of the teens. And then by 1980, we have the established picture of stellar variability. That's pretty fast. People get very upset when nowadays you don't solve a fundamental problem in the space of weeks. But when you consider what kinds of data people were working with and also what conceptual framework they had to struggle against, I think this is really quite remarkable that you go from just barely understanding what the interior of a star is like to understanding the instability of such objects in the space of just about two generations. I think is neat, especially when you got a war in between. So what we were dealing with, what we are dealing with is this. Um, Virtually everything we know about variable stars in bulk comes from the surveys of photometric variability rather than spectroscopic. And the principal reason for that is that the variability can be studied for easily for clusters, but it can't easily be studied for many yet for many objects at a time in the same way that you have for the cadence in photometry. Now, let me make it clear, this is going to change very, very quickly with integral field spectrographs. It's possible as to get every target for which you have a photometric measure you can get a spectrum. That's what's really going to revolutionize this field, especially when it comes to extragalactic. But for the time being, we'll just concentrate on kind of one star at a time and getting some rough idea of what the variability is. So the first thing is these are not symmetric, although some of them are. They have amplitudes that can be a few magnitudes, and there are also color terms in the variations. In addition, the curves can actually get very complicated. This is a set from Ogle and from actually this one I think is from Tess. But in oh, sorry about that. This is from the Gaia DR3. As it, I put these together last night, so a few of them may be a little bit less obvious. Let me zoom in on this. So just looking here at variations of Cepheid variables, you see that the light curves, these are in the Gaia bands, are quite varied. That, yeah, they're asymmetric, and there are amplitudes that are different between the different filters. But the most important thing is the variation that you see in the radial velocities is also very much more complicated, especially for some of these shorter period ones that are being shown, than what you see in just the variation in a binary star. Uh, this kind of radial velocity variation, just to make one point clear, is the sort of thing you would expect if you were looking at, say, a highly elliptical orbit that had some angle of the parastron not equal to 0 or 90 relative to you. But this is not the curve of an eclipsing binary by any means. And so seeing that at the extrema, so at maximum and minimum light, you're at the extrema of the radial velocities. This was actually something that wasn't really expected. Okay, so this is just to summarize with this image using modern data, the kind of conundrum that was facing those who were trying to figure out what was going on. The periods here are covering a relatively small interval from about 7 to about 13 days. And the variation in the shape of the light curve, that is the presence of higher harmonics, isn't necessarily something that goes so simply with the colors and with the period. Okay? But this is just to show one of the samples. Now, okay, the the usual mania in our business is to classify objects or distinguish them by some physical characteristic, some observational characteristic. So in this case, the distinction is going to come here, excuse me, with, okay, one more time. Okay, so the first group to talk about are the ones that are at the highest surface gravity, that are near the main sequence, and that have periods that are substantially less than a day, typically a few hours. These are the so-called Delta Scuti stars or Gamma Dor stars, as usual, named for their prototypes. The Delta Scuti stars are short period. The primary period is usually somewhere in a few hours. It They have low amplitudes, something that's actually very important, and they show more than one mode in the sense that they show more than one period. But the essential point is they sit in the region around the F stars near the main sequence line is at 4, and this is kind of in the region that's traversed by stars in the roughly 1 to a couple of solar mass range. Okay, so these are stars that in their earliest years would have been T-Tauri stars, and they settle down to the main sequence. And for some reason, on the main sequence, they're pulsating. Now, this is not the kind of behavior you expect for normal stars. Uh, at least that's the way we learned it. So when these were first found, they presented a kind of interesting picture because to get one of these to pulsate requires some very specific conditions, namely that the stars sit in this band in the on the main sequence between about of 7 or 8,000 degrees and sorry, so between about 9,000 and 7,000 or 8,000 and about 5,500. So the sun is not in this band. Now, this is to show the next point that after Leavitt's discovery of the period luminosity relation, it was realized that for globular clusters, the group of stars that were called cluster variables, which actually included Cepheids or very, very low mass Cepheids. One of the things that was realized was that, and you've seen this in cluster color magnitude diagrams, on the horizontal branch, so the portion of the diagram where the distribution of stars with color is essentially a constant luminosity or nearly constant brightness in a given filter. There are gaps that are usually shown on these diagrams. That is, you have stars on two sides of a color horizontal branch, which, and this time I can't use, but okay, so I hope you can see this. Yes? No?
Yes, but it's on its side, Steve.
Okay, it's a really primitive form of a color magnitude diagram for a globular, but what I mean by the horizontal branch is that part with the gap. In that gap, there's a group of stars that were already known that here were are known to have periods of about a day, day and a half. They're short period, relatively large amplitude, and characteristic, show the characteristics of a known galactic variable, our Lyra. So it's important to remember here, as usual, that anytime you have one of these classes, it's usually based on a galactic analog. Okay? Um, our Lyra has, as was found by Bailey already in the beginning of the 20th century, and this was from that same survey looking at globular clusters in the southern hemisphere, that there are two different groups, distinct groups. They have the same, roughly the same period, roughly the same brightness, but they're not exactly the same. That one of them, the so-called type AB, shows what look like Cepheid, typically Cepheid-like variations. That is, with a steep rise and a slow decline. And the type so-called C look much more, much more regular, that much more symmetric, but that they also show not just this short-term periodic effect in which these additional harmonics, these additional features are actually stable in the individual stars, but they also show changes in their amplitudes over time without necessarily showing phase drifts. This is the so-called Blotchko effect, the origin of which we still don't know. but that shows that over time, any of these stars may show some fluctuation in their light curves. You have to follow them for some extended period of time, but it looks primarily, not exclusively, like an amplitude variation rather than shifts in periods or shifts in phases. There are also period changes that have been observed in these systems. And we'll get back to that in a few minutes. So the next group is the one that's at the far end of Levitt's original diagram. When you get up to periods over of order 90 days and you start to get to annual type periods, then you get into the group that are called the Myra variables. These are giants. They're high, in other words, they're highly evolved stars. They're on the cool end, so they're on the giant branch. Some of the more extreme versions of these very, very long period variables, like Betelgeuse, are actually on the asymptotic giant branch. So they're more massive and much more, much more unstable. But these are approximately stable with extremely large amplitudes that as one goes up this sequence, going from the main sequence through through the Aurelides, through the Cepheids, and eventually getting to the Myras, you're getting progressively larger amplitudes and also progressively more instability in the light curve. And that's what you can see in the middle part here. This is the actual individual light curve of a couple of cycles from AAVSO of Myra. But this is what happens when you start looking on, say, multi-decade timescales. That, yeah, it's approximately periodic, but these extrema are showing some kind of a statistic. The problem being that the timescale for these variations are of order decades, while observers' patience usually wears thin a little bit sooner. So this is still something that's going to take some time to sort out, like the Blotchko effect, which also happens on decadal rather than daily timescales. This is something that is going to be the future for telescope telescope networks, not just the ones that are doing transients, but you can imagine that for the fainter objects, the observations by the LSST, the Rubin, will be essential because you'll have the full sky covered every couple of days. The problem with that survey is that it's going to be saturated for most of the stars like this. So it's going to be wonderful for looking at stars near the galactic center where you already have some of the surveys like Ogle and Planet and some of the others that were looking for micro lenses, especially Ogle that looks at the Magellanic Clouds. But it's going to be still the realm of automated optical telescopes that, in this case, systematically monitor the sky instead of just looking for transients. These will show up sometimes as transients near the limits of surveys. Like the Myra variables would, in fact, be considered sort of the first transients that were found to be periodic. Because originally, when Myra itself was discovered, it was because it came up above naked eye threshold and otherwise could be below that. So the realization that this was happening periodically was something very important, but it also tells you how the surveys will have to be conducted. They'll have to be aware of the fact that some of these objects that are considered transients are in fact going to turn out to be periodic variables. Uh, Using Myra as the example here, I should recount what you all, I'm sure you all know of the observation in the 20s by, I think it was 23 by Hubble, when he realized that an object that he had marked as a nova in M31 was in fact recurrent. If you read any of the descriptions of the discovery of the periodic variation of a star in Andromeda and the immediate application of the period luminosity relation to get the relative distance of M31 from Andromeda, from the Magellanic Clouds, the thing you may not realize is the hard part was for Hubble to figure out what the period was, largely because the plates that he had weren't taken on precise cadence over a long period because, frankly, he didn't think he was going to see periodic variables. So the discovery of a variable with a period that showed what appeared to be, when you plotted it out, the same sort of variation that the Magellanic Cloud variables that Leavitt had done showed, gave Hubble the tool for finding the distance. It was not an absolute distance because the Magellanic Cloud distance wasn't known, but at least a relative distance based on simple ratio of brightness was easily possible. Okay? So these are other examples. This is from Ogle of different classes of variables. You see that, for example, the Mira here has an amplitude of 5 magnitudes, and this is all done in phases. So this is 246 days. As a comparison, another Mira variable with a 300-day period shows a slightly different light curve and a lower amplitude. So again, the variation in the, the physical characteristics depends on the period, okay? And some of the others, like the ARAS stars, and this one is a half-day period, and this one, which is an AB, is about a half-day period. Okay? All of these are picked up from a single field. Okay? All of these are from the LMC. And so this is the sort of thing that now can be done also for extragalactic systems. That you find that within a stellar population, typical field, you have this whole range of variables. Okay? This is, I think, the most important diagram that's come out of variable star research in the Magellanic Clouds. This is the LMC with the period luminosity relations for the different groups. So the semi-regular variables and the Miras are shown here. They all show some kind, these are some general long period variables, but these are also the shorter period variables. That is, every one of these pulsating stars shows a period luminosity relation. They're not necessarily on the same track, but they all show, they have offsets, but they all show the same basic result. The longer the period, the greater the luminosity. Okay? Uh, I'll skip over the business about periodograms. That's something we can talk about later. Um, so, um, everything okay so far?
Yes.
Yeah.
I don't want to seem boring here. Um, those who have read the Bible, otherwise known as the Hitchhiker's Guide to the Galaxy, will remember that there's the planet forges of Magrathir uh, that gets mentioned as having built planets for uh, particularly discerning uh, consumers. Well, one of the things about building a planet is the same thing as building a star. There are certain mechanical and thermal requirements. So I thought I'd list these as a way of explaining now how we go from this phenomenology that I've been showing you to what is really going on. Okay? So, step one, it's got to be a mechanical balance. You really don't want to build something only to have it fall down as soon as you walk away from it. So that requires that all of the forces, internal and external, that are acting on an object that we're going to call a star have to somehow be balanced. And the way you normally think about this is like with the Earth, that the interior pressure gradient is balancing the weight, Archimedes' principle and all that nonsense. The problem with that is that if you say that the accelerations are zero, you neglect the possibility that something might be mechanically balanced but not static. Okay? Hydrostatic balance implies that there are no internal velocity fields, that there are no accelerations of any kind in the interior, no net accelerations. But we have this other possibility. Something can remain bound and yet have an acceleration. Damn good example of that is an orbiting binary, that it's mechanically bound, but it if it's in an eccentric orbit, there is a radial acceleration. It's simply balanced. So it's something periodic, and periodically there is no acceleration. If you average over a period, the net acceleration is zero, but the velocity is continually changing. Okay? That's important for understanding what it is to build a pulsating star. To pulsate doesn't mean that the star has to, no, let me say it differently. To pulsate requires that something expand and contract. That means it goes through a cycle of accelerations. To be mechanically stable only requires that on a period that averages to zero. Okay? So you can easily build a pulsating water balloon, in other words, an incompressible object that simply changes its shape. That was something that was already worked out in the end of the 19th century by Darwin and continued by just about every mathematician of any quality through the 19th and early 20th century. But the only requirement is that what goes up must come down. Okay? That if you are expanding an object, it must have something internal that causes it to go back. Now, we'll get back to that in just a minute. The second is, and this is where it differs if you're building a star or a planet, you must have thermal balance. And the reason is that stars are essentially ideal gases. Okay, it's true that white dwarfs are not, they don't care about temperature. Well, they sort of do, but not for the bulk of the structure. They're objects that come closer to planets in the sense that they have a pressure that derives only from their density and not from temperature. But for a normal gas, for an ideal gas, if you heat it, the internal pressure goes up, and so the volume is going to have to expand to reach an equilibrium condition to absorb the extra heat. If, on the other hand, when it expands, it's able to get rid of that extra energy, then it's going to contract. This has been known since Carnot, and there's nothing special about it except that when you're building a star, you might have an internal energy source that building a water balloon doesn't have. And that's this point, that ultimately you all know stars are thermonuclear. And so this is the real key to understanding everything that had not been understood at the time of Eddington. Eddington, and also to an extent Rosalind, and certainly Payne-Koposchkin, in the period before about 1950, couldn't really say what was powering the star. Eddington certainly couldn't. And one of the remarkable things about the progress made even up to for the Second World War, with Beta's realization, sorry, Beta and Gamov and Atkinson's realizations that nuclear processing in stellar interiors could actually release sufficient energy to power the stars, to power the luminosity. The one thing that they didn't know or didn't treat was something that Eddington had treated without knowing what the source would be. Eddington and Jeans and Milne and all of the founders of radiative transfer theory, including Rosalind. That is, on the one side, you have the luminosity of the interior that's being generated by the nuclear processes. So energy is being released in the interior, and this is necessarily going to make the interior hot. That means that since the surface is the outside world, that energy is going to have to somehow flow through the star and ultimately be lost from the surface. In other words, exactly the same problem that you have in understanding a planetary atmosphere, namely climate change, is that whatever the energy input is, the outer boundary condition for a star is the same as that for a planet. It's empty. So the only loss mechanism is radiative. Doesn't matter if you have a wind. If you actually were to generate a wind that would carry away all of the interior luminosity, the star would actually be unstable. And so one of the, which gets back to other approximations that we teach students in stellar physics that really don't have much physics behind them. But the important thing is that in addition to the radiation that's going from the interior to the surface, there isn't simply radiative transfer, and it isn't simply conduction. There's another possibility, which you all know very well. It's called boiling. You know, you put the envelope of the star like a pan on top of the flame, which is the core, and if the temperature gradient, if the temperature at the base gets sufficiently high relative to that on the outer parts of the star, this becomes mechanically unstable, but only locally. There are no net accelerations here. It becomes buoyant. One of the most important things about stellar interiors that, let me go here, okay? That, do it here. If you have, this is from a discussion, I just threw this in at the last minute because I can't be sure the pad will work. Uh, but this is a discussion of the Earth, but who cares? If you take a box and you put it on top of a flame and you simply let this absorb heat, then that's going to, by the first law of thermodynamics, which we all know and love, is going to change the internal temperature and then also do work. So this surface, which is a piston, is going to be forced up. Now, we can imagine that there's a region somewhere here below which things are opaque. And the radiation that's coming in is somehow absorbed and heats this plane, imagining this as somewhere in the interior of the star. On that surface, small variations, just perturbations in temperature that are slightly hotter or slightly cooler are going to, because it's a perfect gas in most of the interior, change the internal density. So you're going to have pressure fluctuations because of the temperature, and those are going to give rise to density fluctuations. That, by simple buoyancy, means that the hot stuff is not going to just stay in place. It's going to start rising because it's in a gravitational field. And in that rising, it's going to transport the internal energy, and then this is going to come into play. that the temperature in the interior is going to change as this rises through the background. Okay? And the other way of putting it is we're going to get a change in the enthalpy, which is because you have pressure changes and also because of entropy changes. The thing that's important to consider here is that once you start this process, you're physically, mechanically moving material around. It's not net movement, it's just straight bubbling. Okay? And so here it's the same problem that you have in all of these other cases that if you've got, well, I'm in Pisa, of course, so you got to use the tower for something. Uh, if you want to look at something that's mechanically unstable, you look at the tower if you just let it go for a couple of hundred years. And as it starts tilting, there's a point where the center of mass goes over the critical point in the base and the damn thing falls over. Okay? That's called a mechanical instability. It has a threshold. Okay? It's an inverted pendulum. So is a monopatana, okay, a scooter that although you have idiots who ride these things two or three at a time at high velocity who haven't bothered understanding the principles of mechanics, they will learn that if they go over a certain limit of uh, vertical placement, they're going to fall over. So again, you have a critical point. It's unstable. The other is the density instability that gives rise to the to Archimedes' principle. To make this straightforward, so I hope I'm not boring people with this. If you take two spheres and they have the same mass, and you put a rope between them, okay, so an Atwood machine, as some of you may remember from physics. In that case, if the masses are equal, then when you lower one and raise the other because they're constrained to move, the potential energy that's released in having one go down is equivalent to the work required to raise the other. So when you let them go, they just stay there because they've been in mechanical balance. And it doesn't matter which one moves up or down, okay? That the heavier one, if you now have if they're not equal, in the heavier one, if you lower it, it releases a certain quantity of potential. Okay? That causes, because it's constrained, the other one to do work, to move up. But the lighter mass requires less work than the amount of energy that was available. And so it continues to rise while this one continues to fall. And that's basically Archimedes' principle that if you have two blobs that have the same volume, but one of them has lower mass than the other, in other words, different densities, then the heavier one in moving down releases more potential energy than is required to raise the other by exactly the same amount, as if they are tethered together. Okay? Archimedes found this because he already knew how levers worked. So here, the point is what allows you to transfer energy in a single direction, that is upward, is that this surface is going to be the recipient of the hot gas that's rising, and this surface is going to be the base of the now cooled gas that's sinking. So you're going to get a circulation built up here, which is simply the same as the so-called Rayleigh-Taylor or buoyant instability, that dense stuff sinks relative to light stuff because of this requirement that they're approximately incompressible. And so the volumes that are covered are roughly the same. Now, why do you care about this? I hear you not say. As these bubbles are moving, They're generating sound waves. This is an acoustic medium because it's a compressible medium. So this is a very noisy process. And to make clear just how noisy it is, take a look at this. This is the surface of a wonderful Czech soup that I'm very fond of on my stove, taken at a snapshot where it's convecting. And now I can use the word. This is convection or thermal convection. That here you have regions that are rising, here you have regions that are sinking. This is damn close to incompressible, but the bubbles are being created by the release of fluid, by the release of gases in the fluid. The point is that if this were simply water boiling, you would know damn well when it was boiling because you'd hear it. Okay? That the first thing you hear is the hiss that results from the very, very high frequency bubbles that are formed at the base. But when it's fully boiling, you hear this lower frequency that's being generated that may almost have a harmonic structure. Okay, so far? Because this is what the stellar interior looks like. Remember, I said that it was found that there were stars in certain portions of the color magnitude diagram that are unstable. Not all stars are unstable. Not all stars vary. This is what the surface of the sun looks like. Okay? The sun is not a pulsator, but it pulsates. That the granulation that we see is actually a manifestation of the convection, and the surface does show excited modes, just like this pot does, just like your room does. But this is actually what the interior would look like. You can think of the radiative interior and then a region here. In fact, you can see it. These are convection cells that happen to be rising and condensing. So this is a portion of the atmosphere. Part of it is radiative, part of it is convective, and then you have this layer that in our atmosphere rather conveniently marks where, by condensation, where something changes. You could think of this as an ionization level. But the thing that's important is look at the irregularity of this surface. That is, what you have is the same thing in the atmosphere that you have in that bowl of soup. In other words, you have in convection a conversion of radiative to mechanical energy to, to mechanical motion to transfer energy from the interior, where it is radiatively released by nuclear processes, to the surface, where it is radiatively lost. And the thing that determines where this happens is anywhere that has high opacity. That if you have low opacity, you don't need a strong temperature difference. If you have high opacity, you do. That's why you get boiling at a particular point. The temperature gradient is the thing that's determining everything. That when you have a smooth temperature variation, you don't need convection. You can do things radiatively, which is what you have in an optically thin medium. But if it's optically thick, then the radiation that's hitting this layer, that's streaming into this layer, heats this up, but it's difficult because of the opacity, for the layer to then transfer that energy. Now, you know this. This is the classic example for climate change. You sit in a bed at this time of year, you're freezing, you're shivering, you put the covers on, and after like 20 minutes, you're so hot that you throw the covers off. Okay? The only reason for that is the air next to your body was originally not being constrained in its transfer of energy, by having a highly opaque surface on top of you. You're generating the same amount of energy, but you were heating a larger volume before. And if you put a blanket on it, this is something with low conductivity. So the temperature goes up to the point where you can radiate that energy away. And in fact, you never succeed in that, which is why you throw the covers off. Stars don't. They don't throw the covers off, they convect. And that depends on the particulars of the evolution. So when you're near the main sequence, the hydrogen convection zone is sort of near the surface. The helium convection zone is deeper, that is where helium ionizes. And the same is true for all of the masses of stars. The main sequence has hydrogen convection zones that are near the surface. Okay, so far?
Yeah.
Because this is the zone, the gray zone, where in the interior structure, you hit a critical condition. And every one of these stars in this mass range crosses that zone, sometimes multiple times at different luminosities. The example here in there's a 5 solar mass, which is slightly below where you were, but here on the main sequence, or near the main sequence in the Hertzsprung gap, um, the stars, these are larger than the main sequence, of course, the stars actually cross a region that's unstable. The reason is because you've reached the critical point, which is here, here. Okay? Now, I will get to this point. Let's say you set up a spring and you put a mass on it. You know that the oscillation period depends on two things: the stiffness of the spring, the Hooke constant, and the mass of the blob. Okay? And the greater the mass, the greater the inertia, the longer the period of oscillation for a given stiffness. You can also set this thing up in a way that has variable stiffness along the spring. Okay? That it may be stiff in one place and very loose in another and stiff in another. And so what you get are regions of relative compression and expansion that might not be in phase with each other. Okay? Now, think of what would happen if you had, in a zone that was convecting, sound waves that are going up and down. Now, these are pressure waves, remember? And they may be very large amplitude. In fact, one of the things that happens is as they propagate, the sound waves, as they go into lower density, become steeper. They become stronger for a given amplitude because the density of the background that's supporting them is going down. Now, they're also going to reflect back from the surface in the same way that waves that are compression waves oscillating along the spring are going to reflect back from the upper surface. And if the phasing is right, this can produce a standing wave. And so this is going to have a periodic variability, or any portion in here will have a periodic variability. The same thing can happen here, that when you have the pressure go up, the layer has to lift. When the pressure goes down, the layer falls back. This was the original idea behind pulsating variables according to Eddington. It was a steam engine that the layer, the convection layer, or any layer in the star gets hotter, produces more energy, causes the outer layer to the superior layer to rise, and then if that cycle turns off, this falls back and compresses. In other words, exactly the same thing you have in a steam engine and the same thing you have in a car cylinder. The difference in a car cylinder is that it's an explosive ignition. Then in a steam engine, you hope it's not. Okay? The problem being that this works only if you can figure out why this zone should become unstable. And that's where the calculations come in of the variation of convection with mass and luminosity. That was affected finally by this paper. The first theoretical calculation of the full hydrodynamic pulsating interior of a star. A paper by Christie that I can't say comes out of nowhere, but it was really the first major advance in numerical simulation. This was done with a computer that now would be considered worse than laughable. Uh, the amount of time and the amount of work that went into this is really astonishing. But considering that the basic theory had already been laid by the mid 1960s, I think should give you pause. We really do understand this. And this is what this is what it led to. It was that you could divide the star into zones which were driving and which were dissipating. And dissipation is the radiative zones, and the driving is the convection zones. And in addition, the one thing that couldn't be done in Russellin's book and couldn't be done with the early work on variable stars was that although you could get the variation in the brightness because you would get the variation in the energy output, you couldn't do the dynamics. So you couldn't predict the velocity curves. And when it was finally realized in the 60s that there was a lag between the brightness of the star and the motion of its surface, and that there were also periods introduced that were not the same as the fundamental period. So in other words, you had harmonics, and you can see that in the temperature variation that Christie's models were showing and that all subsequent models show. You have the driving here, which is in time you have very large amplitude changes in the temperature, and then that propagates outward over time this way. In other words, it's a sound wave. Okay, so all of variable stars can be understood this way. And to then make the next leap, we have this. If you want to understand a pulsating star, the best way to do it is to play a tuba or a French horn or a trombone or a trumpet. That is, what you're actually looking at is the surface of the star, which is the same as the open part of the bell, say in a French horn, and different points in the bell where the pressure is changing. So to go back to this diagram, what's happening in the convection zone is the input of noise. Now, noise is broad spectrum. It has all of the frequencies of the turbulent eddies that are characteristic of the soup or of the convection zone at the surface of the sun. Okay? But those waves are going to propagate outward here into an exterior, which is radiative. Okay, the atmosphere and the upper envelope of stars, are, unless they're in the red supergiant phase or giant on the giant branch, are radiative. The layer may be very, very thin, but it, radiative means dissipative. So if you have a convection zone that is radiating noise and it goes into this outer layer, if the layer is sufficiently thin, nothing's going to happen. It's just going to pass the sound. So you're going to see some variations, but nothing's going to potentially resonate. It's going to be like this spring with every one of the parts of the helix having a slightly different strength. But there are conditions where the oscillation that's being driven finds a resonance, a stochastic resonance. In other words, a random resonance where some frequency, because of the sound speed in here, happens to hit a resonant frequency, in which case the layer oscillates. An example that you may have encountered is that is one in a car when you're driving with the windows open at uh, high speed. You may wind up you'll hear the noise that results from the turbulence in the boundary layer at the boundary of the car that is actually causing the air in the interior to respond to the turbulence. In fact, although it's not convective, this is a very good example of what I'm talking about. The turbulence in the boundary layer has, again, a very broad spectrum of frequencies. But one characteristic frequency is is related to the velocity of the car and the size of the window. And in the interior, you have the cabin of the car. So it's possible that the oscillations that are being driven, these random oscillations at the window, actually go into a resonance in the car itself. Uh, I don't know about your experience, but I have a Fiesta that has a wonderful resonance at about 35 or 40 hertz when driving on the autostrada in Italy. And it's really annoying when you hit it because it's very loud. And the only way to stop it is to partially roll up the window, which shifts the frequency of the turbulence off the resonance. Why I'm talking about this is that at different stages in the life of a star, the convection zone is at different depths. And so when it finds itself, any of the convection zones, and every time you go through ionization, that's high opacity. So all ionization zones are convective in the interior. But the one that obviously is the most important because it's the most abundant and it's also the one nearest the surface is going to be hydrogen. Okay? In the sun, it's actually H minus that produces the convection that you see at the solar surface. That's why it doesn't drive the sun as a convective star. Although it is convective, it's only stars that are a little hotter where there's no H minus to worry about, but it's hydrogen that you actually get the pulsation. And that is you have a small, thin radiative layer, maybe a few tenths of a solar mass. And then below it, you have the hydrogen convection zone. And that, people, is the Delta Scuti stars. That here, the convection is from hydrogen at a particular depth. In stars that are hotter, it's closer to the surface. In stars that are cooler, it's deeper. But you happen to have this window in which it hits the right value. Okay? And that's the same thing that I'm showing here. The point of a star is the same as the point of a French horn. The outer boundary is a free boundary. In the case of a room and a brass player, the outer boundary is an open boundary, although it's not at infinity, there's a finite pressure. But this surface is oscillating with a range of pressures. The frequency of that is determined by where in the bell you hit the equilibrium surface with the background pressure. So at very high frequency, you're driving it from the inner part of the bell. At lower frequency, you drive it from the outer part, and the shape of the horn determines the spectrum of the sound. So each one of these has different sounds because of this shape. The analogy in a star is the speed of sound. That what I wrote down here is that the propagation speed is the sound speed, which is the change in pressure with density. It's the compressibility. The dispersion relation is that the frequency is related to the wavelength by the speed of sound. So the frequency is being driven by the convection. What the length is, the critical length where a given frequency can be resonant, is given by the sound speed. In the French horn, it's given by the shape of the horn, where the pressure at that frequency drops. Okay? The other is for those who play flutes, uh, where you put the tone holes. These are actually the equivalent of leaks in pipes. Each one of these, when they're open, is actually lowering the pressure at that point. It's creating the equivalent of a node for the turbulence that's in the pipe. Okay? The demonstration that I'm not joking about this and that is fundamental for understanding stars is this. I take a cylinder. You can do this, and I will probably excite my dog, but you can take a cylinder and simply blow into it, and you get nothing in particular. If you do it with the right pressure, you can actually get a resonance, although it'll be a pretty lousy resonance. On the other hand, if I open it now, instead of a cylinder, you heard that the frequency has now gone up for the same input, which means now the resonance is occurring here, and it's effective that the tube is shorter. Okay? That's the equivalent of changing the sound speed in the stellar interior. Once you understand this, you see why, first, there's a period luminosity relation, because the size of the star is determined by the mass and the luminosity. It's the combination of those. It's the mechanical part. Then where the convection zone occurs is going to depend on the surface conditions and the luminosity in the interior. So the more luminous the star is, in general, the greater the radius is going to have to be, and that is going to shift where the convection zones sit in the star. Okay? But all of this is driven by mechanical and thermodynamical processes. So the gravitational free fall time must enter. That is, this is also then related to the mass and radius of the star through that spring. The more mass you put on top of the spring, the lower the frequency. So if you've got an interior structure that's determined by a luminosity that depends on the mass, you also have the envelope part, the dissipative part, the dead weight part that's sitting on top of the driver that depends on the mass. And so only under specific conditions will that state occur. The example in interior modeling is this. 25 solar mass star. This is just one of those lovely so-called Kippenhahn diagrams. The blue region is excuse me, the blue region is convection, the white region is radiative, and these are nuclear zones. Those aren't important. What is important is this. You see that relative to the surface of the star, there's a convection zone, and then there are multiple convection zones because you have hydrogen and helium, and this is a whole convective envelope. Okay? This is not a pulsating star. This is simply what the interior looks like. But there will be stages in this in the life of this star where this convection zone, like here, has above it just the right amount of mass to fall back in phase with one or more of the frequencies that are being generated in the turbulence. There are many different types of variables because as the period gets longer, the driving becomes more extreme. Because the longer periods are more luminous, that means there's more energy available in each cycle to drive the expansion and contraction of the envelope. So when it falls back with greater force and creates also potentially shock waves and emission that you're going to see spectroscopically. Okay, so now to kind of sum things up because I've been going on for, I'm afraid, a very long time. So stop sharing. Okay, the key for understanding all of this spectroscopically is that the only thing you can do is see what's going on the surface and the regions above it. The advantage is that what's going on in the interior is creating a piston that you call the surface of the star, the photosphere. And so what you're doing, what you're seeing is the waves that are being driven outward from the interior and that are forcing the photosphere to oscillate. Above that is the open atmosphere. That's what you see. You see the compression waves that are passing through that. And because the atmosphere has a much steeper variation in density than the interior, those waves can actually turn into shock waves, which, for example, in our Lyra stars, produces helium emission lines and hydrogen emission. In Myra variables, it produces not only emission in the hydrogen lines, but even in molecules. In Cepheid variables, the short period ones are just going to show the variation of the velocity of the photosphere. But in the longer periods, you can actually see steepening relating to the formation of shocks. So what you're able to see is the reaction of the atmosphere recording the mechanical coupling, which not only is dissipative, but if it's actually steep enough, can drive mass loss. And so the final point is this is what ultimately in the red giants and the red supergiants is responsible for at least part of their mass loss. That you get these strong waves. They're the same thing as waves breaking on a beach. Okay? That in the deep ocean, you don't see the waves breaking. You could have a tsunami and you wouldn't know it except that it's transferring momentum across or energy across a region. But when that energy reaches the steepness of the beach, it suddenly steepens to a shock wave. Okay? That's what you're seeing in the atmosphere. So the periodic monitoring of that phenomenon in the atmosphere is telling you how that energy is going into heating and possibly changing the outer atmosphere. Ultimately, the same thing is connected with what happens with magnetic fields. This is one of the reasons why the solar corona is hot, not because of the shock waves, but because of the fluctuations, the pulsations of the surface being connected to the magnetic field, which is going to generate magnetic waves that are then going to steepen and also reconnect. It's a much more complicated process there, but directly connected with the same physics. Ultimately, what you're doing in stellar pulsations is seeing the conversion locally in the interior of radiative to mechanical work. And then the transfer of that through the structure of the star in a way that ultimately is stable. This is good. That this will affect evolution, that it depends on opacity, and so it depends on metallicity, is very important. It also depends on the rotation of the star. I haven't mentioned the fact that if the star is rapidly rotating, it can't pulsate spherically. It has to pulsate with some higher mode because it isn't spherical. Okay? Non-spherical objects can't behave spherically. So the beta Cephei stars are good examples of stars which are rapidly rotating, distorted, and pulsating. If you have a Cepheid variable in a binary system, then the presence of a tide screws up the period if the stars are close enough. Okay? And we don't know how that works. We also, because there are very few examples that we have available for those, but we do have examples of stars that are in binary systems that do pulsate. We also have examples of stars that are presumably in the instability strip that don't pulsate, that the pulsation itself may not be absolutely stable. It can turn on and off. We'd like to know why. And again, the problem with studying these is the changes are long term. So it involves not only a lot of telescope time, but it also involves persistence. And many astronomers don't have either of them. You do. So this is something that I hope will also serve as an inspiration. Every type of variation we've talked about from the very beginning of our discussions months ago, all are connected with some manifestation of the same thing. Pulsation is actually the quietest of all of the mechanical instabilities that you can have in a star. But ultimately, the most important realization, I think, of the 20th century was that the 19th century picture of equilibrium was wrong, and that we had to expand what we meant by
Mhm.
equilibrium. And perhaps the most important discovery of the 21st century was the broad variety of connections between the different states of instability and the way in which this plays out in ultimately the evolution of the universe, the production of the elements, the dispersal of the elements, the formation of stars, the interaction with the interstellar medium, all of that ties to this same basic picture. So you've been awfully patient, and I'll shut up now and hope that there are some questions. So thank you.
Thank you, Steve. But
Steve, I have a
no,
question.
you don't shut up because we have two questions in the chat.
Oh, good.
Dongli ask, can you explain the difference between linear and non-linear pulsations? In two
Yeah,
minutes.
in like 5 seconds. Linear means there's one period. Nonlinear means it doesn't. It it's grossly periodic. So you can think of the waves that are coming that are just on a surface. So things that look like simple sine waves. Okay. Um, Those don't transfer momentum. They're transferring energy. That is, um, when you see them moving, what they're actually doing is oscillating like vertically in place and then forcing something nearby to oscillate. Okay? That's not transferring mass. It's not transferring momentum. It's just transferring an excitation.
Okay.
But if you have this oscillating with a large enough amplitude, then this one can start to go out of phase with it, in which case it may actually start pulling away. And so you may actually go to the stage of transferring momentum. Now, you know a good example of this because when you look at waves that are coming up to the beach, when they're out in the deep ocean, they're just basically surface bobbing up and down. Okay? That the reason they seem to be moving is because there's something that's driving them, like the wind. But otherwise, if you just had a lake, you could have like a duck going up and down in the middle of the lake, and that would be generating waves that would just like go into a standing wave, but they would just have a single period, okay? But
Mm.
now let those waves go near the bank. And at that point, they start, the amplitude has to rise because the wave has to transfer the same energy. Okay? It's being driven by gravity because it's going up and down like a spring. But as it goes closer to the bank, it has to rise more to lift the fluid to the same level. And that's nonlinear. Basically, it can fall over. That's called a breaker. You know, surfers like nonlinearity. They get bored with linearity. Okay? So I hope that helps.
Okay, thank you. Antoine, can you raise your question to Steve, please?
Yes. Do you hear me correctly?
Yeah, I can hear you.
Yeah.
Thank you. Yes. I don't really understand what happens at the surface boundary of the star.
Okay.
Is it considered as a single medium, the whole star, or there is something happening at, at the boundary, in fact?
Okay. First, when we talk about a surface, remember that stars don't have walls. So you really mean the visible surface, the point where it's optically thick. In other words, the photosphere. If in the first, the simplest picture, that surface is sort of uniform. And forget sunspots. You know the sun is kind of boring. You know, it's sort of a uniform surface. What we can imagine is that in the interior, overall, things average out and it looks spherical at every depth. So when we see the variation of the photosphere in a variable star, it's because that particular optically thick surface has a pressure change below it that's driving it up and down. And so, yeah, it's varying more, sort of uniformly because it's hit that particular resonance. It's the same thing with the French horn. If you could see the variation of the airflow over the opening of the bell, you'd see that at certain frequencies, it looks like it's oscillating regularly. And at other frequencies where it sounds like noise, it looks irregular. Okay? That's the
Mm.
surface, that's the photosphere. Now, if the star is spherical and it behaves the way we've talked about for stellar atmospheres, different wavelengths will give you a probe of different depths. But for stars like the sun, for main sequence stars, the atmosphere is very thin relative to the radius of the star. So small changes in the opacity won't give you very different depths. On the other hand, for giants, if you look in the red or you look in the blue, you're looking at very different depths in the atmosphere. And so you can see phase shifts from the propagation of these waves between different depths, depending on which frequencies you're using.
Okay. Okay, thank you.
This is actually something you see in the line profiles too, in principle, because the wings of the lines, remember, are formed at the photosphere, and the core of the line is formed high up, where the atmosphere is much less opaque. And so different parts of the line profile may actually change. This was something that in the Shapley and Nicholson paper would never have occurred to anybody. They were just looking at a surface and saying, okay, it's moving outward, and so this part's going straight at us, but this part's going at an angle. So the line profile should broaden or shift depending on whether it was expanding or contracting. They didn't think about, in fact, it's only recently that we could do the variation coordinated across the spectrum as a function of time, which probes the way that these different layers are oscillating relative to each other.
And
I'll just add that everything that I've said applies to the Earth's atmosphere. So uh, the waves that I was talking about, if you're in a course in atmospheric physics, you'll hear about Lamb waves, and that's not because Mary had a little lamb, but because Lamb had a little wave, and it propagates upward in the atmosphere and steepens as it goes up in the atmosphere. Uh, Other effects that you know well are acoustic effects, where if you have a temperature inversion, you can hear objects that are far away because the speed of sound is changed in the atmosphere. It's the same thing as an optical illusion, as a mirage. Uh, okay, so all of these effects are all the same. Acoustics and stellar pulsation are the same. Unfortunately, the first people the first work that looked at things like trapped modes used seismograms and seismology as the example. So this gets called astroseismology. It really should be called astroacoustics.
Thank
But
you,
you
Steve.
know, not everybody plays French horns.
Yes, I think it is a corde de chasse, hunting cord.
because in corps de chasse, you don't have pistons, I think.
Um, yes.
Uh,
Actually, bugles are the best example that I know, or post
okay,
horns in English. Um, those are wonderful examples because what you get there is a harmonic series that isn't exactly the same as you would get when you put the valves in. You know, valves are just plumbing. What they're doing is effectively changing the length of the tube. That it allows you with some care to change the length in different ways. That's why you have 3 or 4 valves. And it's the same thing with clarinets and flutes, that when you open and close tone holes, what you're really doing is changing the effective length of the tube. So in a star, that would be like changing that would be like changing the opacity. That if you have a star with very low metallicities, the convection zone is going to occur at a different depth. I didn't mention that the W Virginis stars, for example, are actually Cepheid variables of low metallicity, and they don't have the same periods. They have a period luminosity relation, but their 0 point is different because they have different metallicities, and the convection zone occurs at a different resonant place in different masses. It's really very simple once you realize that these are just musical instruments.
excellent. Thank you very much, Steve. So next time in December, it will be about the late stages of stellar evolution.
And that
As
way
well,
we can talk,
clients.
we can do really nonlinear stuff. Okay?
Okay.
But this is just another chance to say to all of you, just from the bottom of my heart, thank you. I dearly love these sessions and I hope they're useful and that we'll see each other next month. So for those who are on the other side of the pond, best wishes for Turkey Day. And for those who are on this side of the pond, may it be a quiet and peaceful month.
Thank you,
Take care.
Steve.
Take care, Francois.
Thank you,
Thanks.
everybody.
Thank you, Steve.
Night.
Goodbye, guys.
Goodbye.
And
Good night.
stopping the
Thank you.
recording.